question 1, this comes from section 5.2, and it's solving 3 equations, 3 variables. We're going to do elimination method. First, I'm going to take those two, the top equation 1 and equation 3, and eliminate x. Because they already have opposite coefficients. So if I eliminate x, I've got y minus 3z equals -1. But I got to choose 2 other equations, do the same thing. I'm going to choose the second and third equation, but I'll multiply that by 2. Okay. Whoops, that should be a minus 2z. There we go. -4. So if I multiply that middle equation by 2 and then combine it with the bottom equation, end up with that. What does that tell you?
Infinitely many?
Yeah, so this one has infinitely many. So it says here, if there's infinitely many solutions, you've got to state the solution in terms of a parameter, so you parameterize the solution. So you still state infinitely many solutions. And the convention we talked about when we did this a couple weeks ago, when there's 3 variables and 3 equations, you always let z equal t when you're parameterizing if there's infinitely many. So I would start with let z equal t. Then we've got to figure out what y equals. And we have this equation here. And if we make this substitution there, then we could say that y minus 3t equals -1. Then add the 3t over. So now we need to find x. We have z right here. We can choose any one of these 3 equations from the original. I'm going to go ahead and choose the middle one just because it has smaller coefficients. So if I choose that middle equation there, but instead of subtracting y, I'm going to subtract 3t minus 1. Then instead of adding z, I'm going to add t. That's going to equal 2. Then you can combine the -3t and the 1t right there to get -2t. Actually, that should be a +1. My apologies. That should be +1 because you distribute the negative right there. So it should be -2t plus 1. And then the final step there would be to move the terms over to the same side so you get x by itself. So those are the values for x, y, and z. The way you would represent this would be an ordered triple like that. So you'd have 2t plus 1, 3t minus 1, and t. So this is just an example of one of the questions from 5.2. You've got to think of what other kinds of questions came from 5.2. If right here, for example, if that had said like 0 equals 10 or 0 equals anything else, that would be no solution. Yeah. So when you're going through a practice exam like this, think about not just the question being asked, but what section it came from, section 5.2 for this one, for example, and think about what could be different. If this problem changed and the numbers changed or the situation changed, would you still be able to solve it? So rather than saying, yeah, I can solve question number 1, you really should be saying, yeah, I can solve a system of 3 equations with 3 variables using the elimination method. Really, that's what question 1 is about, is solving a system of 3 equations with 3 variables. Question 2 is from 5.3, where it was partial fraction decomposition. So there were 2 types of questions we did in 5.3. One of them said find the form of the partial fraction. That's where you just have to leave it in A over something plus B over something. That's called the form of it. But this one actually says find the partial fraction decomposition. So we've got to solve for the values of A and B and go the whole process there. The first step would be to factor the denominator, but this one is already factored. But just be aware, if the denominator is not factored, then that's where you're going to start. You're going to try to factor that into its individual factors. Reason for that is the number of factors, remember, is going to determine. Well, let me ask you guys, what does it determine? What does it mean that has 2 factors here? It's been a while since we've done partial fractions.
Wouldn't it be like A and B thing?
Yeah, it means it has 2 pieces. Yeah, exactly. It means it has A and B. And then the denominator is just the separate factors. So if the question had said find the form of the partial fraction, you'd be done. This would be the form of it. But this one says actually find the partial fraction. So now we've got to do those other couple of steps and solve for A and B. So the next step, if you remember, was to multiply the whole equation by the lowest common denominator, which is always going to be your original denominator in factored form, always. So then when that denominator multiplies or distributes all the way to there, the whole denominator would cross out. So you're just left with 9x minus 11 on that left side. When it distributes to that partial fraction with the A, the x minus 3's would cancel. So then A distributes to x plus 5. And then when the lowest common denominator distributes to the B partial fraction there, then the x plus 5 would cancel. So then B distributes to x minus 3. So then at this point, because it doesn't matter what x equals, we're not solving for x, we're solving for a and b. If you remember, this is where we chose values for x, and we're not choosing random x values, we're choosing what I call convenient values. For example, with this one, if we let x equal -5, and if you plug it in there, it's going to cancel out that part of the equation because you'd have 0 plus a, or 0 times a, which is 0. So I'm going to let x equal -5 and plug it in for every x in the equation, all three of them, right there. So on the left side, you get 9 times -5, it's -45. And then subtract 11, you get -56. A is going to disappear because you get 0 times a. But then -5 here minus 3 is -8 times b. So then we get b equals 7. Then we're going to do that exact same process, but with a different value of x, because we've already solved for b. Now we got to solve for a, which means I want b to disappear this time. So to make b disappear, I'm going to let x equal 3. Because if I plug a 3 in right there, you get 0 times b, which makes b disappear. So you're going to want to plug 3 in for all the values of x again. 9 times 3 would be 27, minus 11, that's 16. And then a 3 right there, 3 plus 5 is 8. So you have 8a. B disappears because you have 0 times b. So you have a equals 2. Hey, David.
Hey, what's up?
How you doing?
All right.
Good. We just started. We're on question 2 of the practice exam.
Okay.
And this is recording, so you can go back after we're done and you can see the recording for anything that you missed.
All right, sweet.
So now we have a and b. We just rewrite our partial fractions. So it's 2 over x minus 3 plus 7. Over x plus 5. And as far as questions from 5.3, they really don't differ much from something like this. The only thing maybe that could be different is your denominator might not be in factored form to begin with, so you just have to factor it first to see how many factors you have, which will determine the number of partial fractions. Question 3 is from 5.4, solving systems of nonlinear equations. There's 2 methods you really want to be familiar with from this section. It's solving using the elimination method or solving using substitution. So I'm actually going to do this one twice, the same problem twice using each method so you can see how to use elimination or substitution. So first, if we do this using elimination, the only variable that would even eliminate would be that one right there, 6x or 3x, because those are like terms. I wouldn't be able to eliminate this column because those aren't like terms. So if I wanted x to eliminate, I'd have to multiply by -2. So then the system turns into 6x plus y squared equals 10. That top equation doesn't change, but the bottom equation is -6x plus 2y equals -10. Now x eliminates, and you've got to be careful with this column because they're still not like terms. You can't combine them into one term. You'd have to write it as y squared plus 2y equals 0. So now we have a quadratic equation. Normally quadratic equations have 3 terms, and you'd have to solve using factoring or the quadratic formula. This one only has 2 terms, and they both have a y as a common factor. So one way you could solve this is factoring out a y. If there do happen to be 3 terms, which is actually more common, let me actually back up a step and see how far back do I want to go. Let's say, for example, there was a number here. I know there isn't, but let's say there was a 4. What would you do with the 4?
Subtract it to the other side.
You subtract it over, get it equal to 0, and then most likely solve by factoring, right? That's more common. So that's something to be aware of and be prepared for. But this one was already equal to 0, and it only had 2 terms. That's why we're factoring out like that. And then we still have 2 factors. Each factor is going to give us a solution. The first factor of y means that y is equal to 0. The second factor, y plus 2, means that y equals negative 2. So we've only solved for y. We still have to solve for x. We're going to get 2 solutions here. One of them is going to be something comma 0. The other one is going to be something comma negative 2. So we just got to find the matching x values for those y values. That's where you would go to your original equation. That one, for example. If I start by plugging in a 0 for y, because one of my y values was 0 right there, if I plug in a 0, then I get 3x equals 5. So x equals 5/3. If I plug in the negative 2 for y, then I get 3x plus 2 equals 5. If I subtract 2 and divide by 3, I'm going to get an x equals 1. So that's solving using elimination, and that only worked because you had like terms right there. Not that you have to do substitution on this one. Elimination is fine, but there are some systems of nonlinear equations where elimination method doesn't work. For example, if this were a 3x squared right there, then the x column couldn't eliminate because those wouldn't be like terms, and the y column still wouldn't eliminate. So you do need to also be prepared to solve a nonlinear system using substitution. What I would do for that, just take that bottom equation there and rearrange it so y is by itself. So if you moved y to the right side and 5 to the left, essentially just switch their places. That bottom equation becomes y equals 3x minus 5. And then the top equation stayed the same. And the reason for getting y by itself is you could substitute that value in for y right there. And then you would write it as 6x plus, instead of y squared, you have 3x minus 5 squared equals 10. And I do tend to see quite a few mistakes with something like this, 3x minus 5 squared. Remember, you can't just distribute that exponent. 3x minus 5 squared means 3x minus 5 times 3x minus 5. And if you use the distributive property correctly, you would get 9x squared, let's see, minus 30x plus 25. If you were to distribute that right there correctly, that's what you should get. All right, once we get to this step, we'd combine any like terms we have. He does go into all of them, so we could factor out a 3, which should give us smaller coefficients. That'll work. And we could actually just divide by that 3 to get rid of it, because on the right side, 0 divided by 3 stays 0. So I'm just going to go ahead. I'm just going to go ahead and get rid of that 3 altogether. And then I think we're going to have to factor this. 3 times 5 is 15, so we need factors of 15 that add to negative 8. And that's going to be negative 5 and negative 3. So what we do, this is just factor by grouping. We split up that middle term into these two numbers here, 3 and 5. So I'm going to rewrite that as 3x squared minus 3x minus 5x plus 5. I'm just splitting up that middle term into these two numbers right here. This is that factor by grouping method. Then group those first two terms, and you can pull out a 3x. That leaves you with x minus 1. And then from those two terms, you could factor out a negative 5, which would also leave you with x minus 1. So then your two factors are 3x minus 5 and x minus 1. So then the two values for x are x equals 5/3 and x equals 1. So we have two values of x, we're just missing the values for y. And those values for y we can find right here with the equation we started with, y equals 3x minus 5. Now you can just plug in your x values. If I plug in the 1, for example, right here, 3 minus 5 is negative 2. So one of our y values is negative 2. That came from x equals 1. And if I plug in the 5/3 right there for x, the 3's would cancel, so you get 5 minus 5, which is 0. And I hope we got the same solution both times. Did we get the same solution both times?
Yeah. Oh, well. Yeah.
Looks like we do. All right. I know that took a lot longer than necessary, but depending on what the system looks like on the exam from section 5.4, you may not be able to use elimination, or you may not be able to use substitution. You just have to make a choice, so you need to be prepared to use either. I've made a change on question 4 to when we originally learned it. This was from section 5.5. I've made a change here. It says you do not need to label the vertices with their coordinates. When we took notes on this, I don't know if you remember, but let's say we had a circle with a line going through it. When we first did this, I had you find the location of those vertices. Is this ringing a bell?
Yeah.
Yeah.
Now, for question 4 on the practice exam and on the exam itself, you're not going to need to find the coordinates of those vertices. All you're going to have to find is the double shaded region. That's what the solution set is just the shaded region. So it should be a little quicker now, not having to find those vertices. It just basically turns into a graphing problem. So that first inequality, x squared plus y squared, anytime you have x squared plus y squared equals 9 in this case, it's a circle when you have both variables being squared. So it's a circle. That number at the end means that the radius is 3. You take the square root of that number. So it's a circle with radius 3. And a circle has a center. The center points, any circle that we had to graph in section 5.5, the center point of that circle was always at the origin right there. So this top inequality is a circle with the center point at the origin.
Okay.
And it has a radius of 3. So I would just go 3 points on all axes there. And one common mistake students make on a problem like this is forgetting to look at the inequalities. If there's no equal to part of the inequality, then it's got to be a dotted line rather than a solid line. So since it's just less than 9, I'm going to use a dotted. And that's a terrible looking circle. It's more of an oval, but it's a circle. Use your imagination. If now that's how to graph a circle. Let's talk about, well, I guess we have that down here. I was going to say, if only one of the variables is squared, if x is squared and y is not squared, then that's a parabola. So this one down here, we're going to actually be graphing as a parabola. But let me go back up to here. We still haven't shaded yet. We've got the circle on there, but not the shaded region. So I'm going to use a test point of 0, 0 and plug 0 in for both x and y. And you end up with 0's less than 9, which is true. So for that top inequality, we're shading inside the circle, not outside. So I'm just putting little arrows here to remind me we're shading inside. Now the bottom inequality, because it's just x squared, I'm going to rewrite it as y is less than negative x squared plus 3. It's going to be easier to graph if you write it like that. And now this is taking us way back to chapter 2, I think, when we learned transformations of functions. This plus 3, it's outside the function, so it's going to move the graph up 3 units. That minus sign in front of the x squared is a vertical reflection, so it's going to flip the parabola upside down. So the parabola has a vertex actually right here at 0, 3. And it's facing upside down, so it's eventually going to look something like that, but need to have the correct width. So I'm going to find out where the parabola is when x equals 1 or when x equals negative 1. So if I plug a 1 in for x, for example, 1 squared is 1, and then you multiply it by negative 1, so then it becomes negative 1. Negative 1 plus 3 is 2. So we have 1, 2 and negative 1, 2. And again, because it's just less than and not less than or equal to, it's got to be dotted. So make sure to make that a dotted parabola, not a solid. And then we can use that same test point right there, 0, 0, since none of the graphs go through it. So if I plug in a 0 for y and a 0 for x, I get 0 is less than 3. That's also true. So we've got to shade inside the parabola and inside the circle. That's going to be our solution set. Inside the parabola, inside the circle. So that's this little piece right here. That's what it means to graph the solution set. And since we don't need to label the vertices, we don't have to find out those coordinates of those intersection points right there. Yay, right?
Mm-hmm.
Really, the only thing that could be different on a problem like this would be if they were equal instead of just less than, you would remember to make those solid graphs rather than dotted. And then these graphs could be any variation. It could be a quadratic with a linear, like a straight line. It could be a circle and a straight line. It could be 2 quadratics or 2 parabolas. But at any rate, you graph the solution set means you find the shaded region that's the same with all the graphs. Number 5 was something we called linear programming. It was part of section 5.5, but it was in the back of chapter 5 on page 42, I think is when it started. Linear programming. So if you remember our discussion there, what we start with is called the objective function. That isn't graphed. You don't graph the objective function. You use these constraints to make a graph here that is going to have some kind of a shaded region, and then you find the vertices of that shaded region, and you plug those vertices into the objective function. That's how this works. And this objective function here is z equals, it could be any value, it could be p, it could be y, it could be any variable there. So maximize the objective function according to these constraints. So we're going to start by graphing that system of inequalities. So top one there, x is greater than or equal to 0. Anytime you have x equals a number, that's a vertical line straight up and down. So that one, and it's greater than or equal to, so it's a solid one. So that is this line right here. This is the line x equals 0. And greater than 0 means shading to the right of that line, so we're going to be eventually shading to the right. The next one here, negative x plus 4. That's in slope-intercept form. So your y-intercept is 4, and then the slope is negative 1. So you'd go down 1 over 1, down 1, over 1. And it's also equal to, so I can go ahead and use a solid line rather than a dotted line. And you notice I've only graphed the portion of the line where x is greater than 0. I didn't graph this portion of the line here because we already know that x has to be greater than 0, so you don't need to worry about when x is less than 0. And we'd want to figure out where to shade on that one. So if you use your test point 0, 0 and plug a 0 in for both x and y, then you have 0 is less than or equal to 4, which is true. So you'd be shading beneath that line. Now that last one there, y greater than or equal to x, there's no plus or minus anything for a y-intercept, so that means the y-intercept is 0. And then the slope is 1. You go up 1, over 1, up 1, over 1. And I'm using a solid line because I have an equal to. It's greater than or equal to. And y greater than x would mean you're shading above that one. So the feasible region, or the solution set with linear programming is called the feasible region, would be the portion that contains all three of the shaded areas, and that would be this little triangle. So that's called the feasible region. Now, what we do with that feasible region, if you remember, is you find the corner points. Those are called the vertices, and you plug those into the objective function, and it says maximize, so we want to find the biggest value of z. So we need to find each location there. Some of them are easier to find. Like that one obviously is 0, 0. This one here is 0, 4. That one there is the intersection of two lines. We have this line and that line. Typically, when you're trying to find an intersection point by two lines, you have to solve a system of equations that generated those two lines. So if we have a system of equations now, y equals negative x plus 4 and y equals x, we could solve that system of equations to figure out the location of those two x and y values. I know this one seems obvious. It's going to turn out to be 2, 2, 2, 2, just because of the graph, but if this were a different problem, this is how you would find it. You would have to solve a system of equations, find that intersection point. So if y equals x, then I could substitute a y right there for this x. So I could have y equals negative y plus 4. And then add a y over to get 2y equals 4. So I know y equals 2. And it says right here that x and y are the same, y equals x. So if y is 2, then x is 2. So once we have all the coordinates of the feasible region, then we have to find the value of z for each of those coordinates. So I need z for 0, 0, for 0, 4, and for 2, 2, to see which one's going to give me the biggest value. So the first time around for 0, 0, I get 4 times 0 plus 3 times 0, which is 0. I'm just plugging it in right here to the objective function. For 0, 4, I get 4 times 0 plus 3 times 4, which is 12. And let's see, for 2, 2, I'm going to get 4 times 2 plus 3 times 2. That's 8 plus 6. So that right there is the maximum value. 2, 2 maximizes the objective function z. It's been a long while since we've done something like that. It won't vary much on an exam. Really, the only thing that may be different would be your starting inequalities. So something to keep in mind. these were already in slope-intercept form, which may make them easier to graph. It is also possible that these are given in standard form, so something like 2x plus 3y is less than 6. So you're going to want to be familiar with how to graph a line when it's in standard form like this, as well as if it's in slope-intercept form. Does that make sense?
Yeah.
But other than that, it's not going to be, there's not too much difference you can expect there on something from linear programming. I know on the homework, there were some story problems where you had to generate the objective function first and then generate your constraints on your own. A linear programming question on an exam will already be set up like this, where you just have to graph it and find the vertices, plug them into the objective function. Oh boy, we're getting into the fun stuff here. Section 6.1, solving a system of linear equations using Gaussian elimination. Now I need to make sure, and hopefully you're listening very carefully, if it says solve the system of linear equations using Gaussian elimination, you must show that you have solved it using Gaussian elimination. If you use another method, even though you may have the right answers, if you use any other method, or if you don't show any work and just have solutions, I can't give you credit. The credit here is given by knowing how to use Gaussian elimination. So make sure that you're showing your work, that you're using Gaussian elimination. What that means is you set up the augmented matrix. And reduce the matrix to row echelon form using row operations. So I'm going to try to get, well, we already have a 1 right there. That would be your first goal, is to get a 1 right there. But after that, you want to get those to be zeros. So I'm going to multiply row 1 by -2, add it to row 2. That's going to become a new row 2. So -2 times 1 is -2. -2 plus 2 is 0. -2 times 2 is -4, and -4 minus 1 is -5. -2 times -1 is 2. 2 plus 3 is 5, and then -2 times 6 is -12. -12 plus -13 is -25. Now I need to get that 3 to be a 0. The only thing you can add to it is -3, so I'm going to multiply row 1 by -3 and add it to row 3 and give myself a new row 3. So now 1 times -3 is -3, plus 3 is 0. 2 times -3 is -6, -6 plus -2, -8. -1 times -3 is 3, 3 plus 3 is 6. And then -3 times 6 is -18. -18 plus -16 is -34. Now I want to get a 1 right there. So I can multiply row 2 by -1/5. That would give me a new row 2. Now I need to get this to be a 0. And I can use this 1 above it. If I multiply that 1 by 8 and then add 8 plus -8 is 0. So what I need to do is multiply row 2 by 8 and add that to row 3 to give me a new row 3. So 8 times 0 is 0, 0 plus 0 is 0. 8 times 1 is 8, 8 plus negative 8 is 0. 8 times negative 1 is negative 8, negative 8 plus 6 is negative 2. And then 8 times 5 is 40. 40 plus negative 34 is 6. And technically speaking, we're not all the way to row echelon form because we don't have a diagonal of all ones right there, but we're to a point where we can start to backward substitute, because this bottom row represents the equation negative 2z equals 6, and if we divide by the negative 2, we get z equals negative 3. And then we can take this middle row, which represents the equation y minus z equals 5. And if we substitute the negative 3 for z, we get y equals 2. And then we could take that top row, which represents the equation x plus 2y, but y, remember, now is 2, and then minus, instead of minus z, remember z is negative 3, and that equals 6. So we have x plus 4 plus 3 equals 6. So x equals negative 1. Okay, question 7 was from 6.2, operations on matrices. We have matrix multiplication, we have matrix addition, subtraction, and then scalar multiplication. So A times B, A is a 3 by 3, B is a 2 by 3. Those aren't matching numbers there. So A times B is not possible. Now B times A, here we have a 2 by 3, and A is a 3 by 3, so we have B times A here. So the inner dimensions are the same, so that means the multiplication is possible. And it's going to result in a 2 by 3. So 2 rows, 3 columns. So row 1, column 1 is going to be row 1, column 1. So we're going to have 1 times 0, which is 0, and then 2 times 0, which is 0, and then 1 times 5, which is 5. This entry right here is row 1, column 2, so I need row 1, column 2 right here. So that's 0 times 1, which is 0, 2 times 3, which is 6, and then 1 times 0, which is 0. This entry right here is row 1, column 3, so I need row 1, column 3. So 0 times negative 1 is 0, 2 times 1 is 2, and 1 times negative 2 is negative 2. Now that entry right there is row 2, column 1. So row 2, I need row 2 here in column 1. So it's 3 times 1 plus negative 2 times 0 plus 4 times 5. Now I need row 2, column 2. So row 2, column 2 there. So that's going to be 3 times 1 plus negative 2 times 3 plus 4 times 0. And finally, I need row 2, column 3. This will be 3 times negative 1 plus negative 2 times 1 plus 4 times negative 2. Okay, subtracting 2b minus 3c. Adding or subtracting, the matrices have to have the exact same dimensions. So if we're talking about b and c, they're both 2 by 3s. So they have matching dimensions. So 2 times b just means the b matrix with every entry increased by a factor of 2. So 0, 4, 2, 6, negative 4, and 8. This is 2b. I just multiplied b by 2. Now 3c means everything in c gets multiplied by 3. So negative 9, 6, 12, negative 3, 0, 21. So this is 3b, or 3c rather. And now it's just subtracting entries that are in the same spot. So 0 minus negative 9 is 9, 4 minus 6, negative 2, 2 minus 12, negative 10, 6 minus negative 3 is 9, negative 4 minus 0 is negative 4, and then 8 minus 21 is negative 13.
So question 8 is from section 6.3. And again, pay particular attention to the directions. If it says solve the system using matrix equations, then that is the method you have to show. It's not sufficient just to show a solution, you have to show the process. So matrix equations is the process of creating different matrices from this system of equations. Remember, we have an A matrix, which is our coefficient matrix, and then we have a matrix containing the variables, which I'm going to represent with just a variable x, and then we have a matrix containing those constants there, the 10 and the 30, and I'm going to represent that using the letter B. And then to solve for this matrix here, the matrix containing the variables, remember we need to multiply by the inverse of A on both sides of the equation, because when you take a matrix and multiply it by its inverse, that cancels in a way the matrix, or reduces it to the identity matrix rather, leaving us our variable matrix. So that's the process that we need to show. Matrix A, remember, is the coefficient matrix and so what we have then is this matrix equation that looks like this. So we have matrix A, we have matrix X, and we have matrix B. So what we need to do is multiply by the inverse here and multiply by the inverse here. And really this is what we're showing. A inverse times B is equal to x and y. So first order business is to find the inverse of A. And the formula is 1 over AD minus BC, which turns out to be the determinant, which we learned about in section 6.4. And then D and A switch spots, and then B and C change signs. So 1 over A times D, this is A and D right here, the 4 and the negative 2. So 4 times negative 2 is negative 8. And then subtract B times C is right here, 3 times negative 3. That's negative 9. And then the negative 2 and the 4 change places. And then here, these numbers don't change places, they just switch signs. So the negative 3 becomes positive 3 up there. And then in the bottom left corner, the positive 3 becomes negative 3. Then right here, subtract negative 9 is plus 9. So negative 8 plus 9 is 1. 1 divided by 1 is 1. So the coefficient here in front of the inverse matrix just changes to 1. And remember in the lesson video for section 6.3, oftentimes, more often than not, you're going to have some kind of a fraction like 1/3 or 1/5 or negative 1/10. It is best to keep that fraction outside of the matrix rather than multiplying it into the inverse matrix, because it makes the multiplication easier. So at this point, now that we know the inverse of A, we need to show this operation right here, the inverse of A times B. So the inverse of A times B is equal to our inverse, which is technically it's 1 over 1, but 1 divided by 1 is just 1, so I don't need that coefficient. But then we have the negative 2, negative 3, 3, 4, so there's the inverse of A, and then I'm going to multiply that with matrix B, which is 10 and 30. Now, this is a 2 by 2, this is a 2 by 1, the inside dimensions match. The outside dimensions say that we're going to get a 2 by 1 matrix out of this multiplication. So 2 rows, 1 column. So this entry right here is in row 1, column 1, so I need row 1, column 1. So that's going to be negative 2 times 10, which is negative 20, and then that's going to be 3 times 30, which is 90. Now, the next entry, this entry right here is row 2, column 1, so I need row 2 and column 1, so that's going to be negative 3 times 10, which is negative 30, and then 4 times 30, which is 120, and then we simplify. So that top entry is negative 20 plus 90, that's 70, and then negative 30 plus 120 is 90. Now at this point, again, if there had been some kind of a fraction coefficient in front of my inverse matrix, that's when you would take that fraction coefficient and multiply it into there. But since we just had 1, we don't need to do that in this case. So what we have then is xy is equal to 70 for x and 90 for y, which means our solution is x equals 70 and y equals 90. And if we wanted to check that, which wouldn't be a bad idea, 4 times 70 up here in the original equation, 4 times 70 is 280, 3 times 90 is 270. If you subtract those, you get 10. And then 3 times 70 is 210, and then 2 times 90 is 180, and if you subtract 210 and 180, you get 30. So the solutions check out.
Question 9 and number 10, for that matter, they both come from section 6.4. 6.4, calculate the determinant of the matrix. If you have watched the video, I showed you 2 different ways to find the determinant of a 3 by 3 matrix, and you can do either one, either method. I'm going to do the method where you take these first two columns and repeat them onto the right side here. So 2, 3, 4, and 1, -7, -6. And then you have to go in the same order here. You always start at the top left and find these products here. So 2 times -7 times 0 is 0, and you always add when you go in this direction. 1 times 0 times 4 is 0. And then this one here, -5 times 3 is -15. -15 times 6 is 90. Let's see, 15 times 6. Yeah, that's 90. So 90. Now we have to find these products. Didn't want to do that. Here. And those ones we subtract. So subtract, and then the first one here, 4 times -7 times -5. That's 35 times 4. That's 140. So we're subtracting 140. This one here is 0, so we minus 0. This one here is 0, so we minus 0. Important thing to remember is when you're going in this direction, those ones you add. This direction here, those ones you subtract, which is something to remember. So we have 90 minus 140. Which is -50. Okay, last, we have number 10 here somewhere. Here we go. Okay, you must use Cramer's rule. That's what the directions say. If you find the solutions any other way, even if they are correct solutions, you can't get credit for this problem. You have to solve it using the specified method. So Cramer's rule uses a series of determinants. So D is going to be the determinant of just the coefficients. D sub x would be a determinant where the x values here have been replaced with these values. So -1, -31. And then D sub y is where these values go into the y column. So this first determinant is AD, which is 12, minus BC, which is -10. This determinant is AD minus BC, and this one is AD minus BC, and then once you have those three determinants, you can solve using Cramer's rule. And then y is d sub y divided by d. So this is saying that x is equal to -3 and y is equal to -4, which again, as you saw with the last problem, it's always a good idea to check. So that one, we'd have 3 times -3 minus 2 times -4. So this is -9 plus 8, which is -1. Looks like it checks out.